Thank you very much for the introduction, and also I thank the organizers for arranging such a beautiful research program and giving me the opportunity to talk about Feynman propagators on a curved spacetime. So this is based on a joint work with Alex Strohmaier, and it's available in arXiv. It's also accepted, but not yet published. So to begin with, let me start with some motivation. So we consider, say, wave operator on Minkowski spacetime. It denotes just by box. And in coordinates, we can write it dt square minus t by t underscore x. So I mean the spatial part. And if you like, you can put mass, but not important. So this is x on. I will act well a smooth setting. So d-dimensional Minkowski spacetime reversal. Now this is a hyperbolic operator, so it's not invertible, as we all know. And apparently there is this notion of propagators or Green's operator. So let me just recall it so that we all are in the same footing. So by a propagator, I mean a Green's operator, which means it's a mapping from compactly supported functions on Rd to spatially compact smooth functions on Rd. So by spatially compact, I mean these are smooth functions, but its support is contained in causal future and past of some compact set. Okay, such that we apply the box on G, then is the identity operator. And this is same as if we act G on box, but now due to matching of the domain, we have to restrict on compactly supported functions. Okay, so as we all know, it's a classical thing. We have causal structure on Minkowski spacetime. So we have causal future and past. And based on that, we have, say, more tagging. So I give by x. One tagging is the retarded or advanced. And these are, they satisfy this property, plus their support is in either in causal future or causal past, depending on your test. And one can literally write these things very explicitly. So for instance, formally, because what I'm going to write an oscillatory integral, but one can smear it with first function and then everything is nice, but let me use this sloppy notation for the time being and integrate over here. Okay, so Rd minus 1 e to the power minus I E. So E is the energy, T minus S minus e to the power plus I T S. And we are taking integration over I. So this is again a spatial part, x t psi divided by 2 pi to the power t minus 1 to e. Okay, so that's fairly explicit, as we can see. Now one can ask, okay, how about these things if we look for an Lorentzian setting? So let me now go there. So now we are in a Lorentzian world. So I give the calligraphic M. G is a globally hyperbolic spacetime. So by curved spacetime, I will always mean a globally hyperbolic spacetime because we have existence and uniqueness of these propagators only for globally hyperbolic spacetime. And to be in the same footing by a spacetime, I mean it's a connected and time-oriented Lorentzian manifold. Now we consider a vector bundle E over M. So this is a complex smooth vector bundle. Now, there are several names of appropriate generalization of wave operator. So one can call wave type operator or normal hyperbolic operator. So let me use normal hyperbolic operator. Also, let me use the shorthand. So a normal hyperbolic operator is a second order differential operator. I use same notation as box here because that one will be a special case of this one, which acts on smooth sections on the vector bundle to itself. And it is called normal hyperbolic if this principal symbol is given by the spacetime metric. And identity for bundle endomorphism. So you can pick your favorite bundle, and then you have say, the most general form of a wave type operator. You can write locally, then it has G mu nu with this expression and then potential term. So you can put mass or potential. Everything is included here. Okay. Now we ask similar question, propagator. So same expression. Now we have this smooth sections and all these things and these properties. And apparently it's a classic result by Hadamard. So it's fairly old and written in French, which I cannot read, of course. So I haven't read it. And then there is also a large paper by Rees. One of these is also in French, which I didn't read either. And 200-something pages. Okay, so I know from other references that these two people constructed in a great generality of advanced and retarded propagator. Okay, so they tells that there exists unique, retarded, and advanced propagators. Okay, and if you look more modern version where I read, there is this nice book by Gunther and also more recent and geometry flavor, the Bear, Brafligino. Okay, so now the question one can ask, okay, are these all or we have more propagators? So apparently, if I am not mistaken, also I am not an historian, probably in maths community, or at least in PDE community, only these two were known. And then Mr. Feynman in 1948, he used some quantum field theoretic argument. So he was using this sort of notion like, if you use this as a Klein-Gordon operator on distributions, and then it describes some quantum field, and then you have in Minkowski corresponds between field and particle. So Striegelberg has this already understanding that particles are moving in time, and then he somehow philosophized that, okay, there are antiparticles that Dirac invented, and they move backward in time. And Feynman really put forwarded his work, and he wrote something like this. Again, I am writing as an oscillatory integral, so it has to be understood in the sense of distribution. Theta minus s e to the power minus I e minus s plus the Heaviside theta, now the other way, s minus t e to the power I e minus s, and everything integrated as before, I e Euclidean part divided by pi to the power t minus 1 to e. Okay, so the main message of this expression is that if you look at here, what advanced and retarded are doing, they take positive energy or frequency solution and then they put forward in time or backward in time. Okay. But what Feynman did, he kind of combined these two in the sense that it takes sort of frequency splitting. It takes positive frequency to forward in time and then other negative in time. Okay, you can also rotate, then sometimes it's called anti-Feynman, but I will just use Feynman. But everything is here. Now, this question was naturally motivated in maths, or in fact in physics community, that well, what is really this a proper definition, or how one can formalize this thing. And again, I'm not an historian, but apparently this is very non-trivial, because what Feynman used is basically Fourier transform. Now in a manifold, you can't do Fourier transform. Okay, and then he used this splitting based on positive and negative particle antiparticles. But on a space-time, you don't have a notion of energy, even positive and negative, unless you have a killing vector field, which in general we don't have. So from very conceptual viewpoint, like how one can generalize these things is very non-trivial. And apparently this non-trivial question was asked to Lord Hurmander, maybe also before people, but at least what I read in his paper by Whiteman, that what can be this case. So in their Fourier integral operator 2 paper that what Hurmander wrote, that this question was asked by Whiteman to him. And to answer this question, Hurmander used some tools that he developed only 2 years before. So let me introduce some tool to formulate that. So tools. So in the summer school, this was discussed, I think, by several lectures, one by Alexis Strohmaier and then by others, that this notion of wavefront set. So just I briefly recall in case anyone is not familiar. So we consider U, the distribution on capital U, where capital U is an open set of Euclidean space Rd. And then by T star U, and I will put a dot, which means that it's a cotangent bundle over U, but the zero section is removed. So any element in this bundle, X0, C0, which is an element of here, is not in the wavefront set of this distribution if and only if. So this is due to Hurmander's ICM lecture, and similar idea was developed by Sato 1 year before, but in analytic setting. Okay, so if there exists a compactly supported function on U with f of x0 identically 1, and there exists an open conic neighborhood. Let me write NBH for neighborhood with this sort of calligraphic U of this vector or covector C0, such that so we take Fourier transform of this distribution U, and we somehow localized using this F, so F of U. And if this satisfies this bound, so 1 plus psi, by norm I mean that just sum of all the components, so C1, C2, dot, CD, power n, and then we take supremum over all U. If this is bounded for any capital N goes to N. Then, okay, I wrote a bit messy way, but hopefully you don't mind. So if this bound is satisfied, then it's not in the wavefront set. Otherwise, it is in a wavefront set. So if some of you are not familiar already with this concept, maybe it looks a bit wordy. So intuitively, I found this example nice. So we can think about this part. So if an ant or we are moving in this direction, so at here, we'll see there is a very stiff thing, and so we'll have some obstruction. So if you look at it in terms of differentiability, you'll see there is abrupt change. But in the same point, if someone moving in this direction, then it will never encounter any non-smoothness. So what wavefront set does, it tells in which point there is this sort of situation and in which direction. So it encodes more information, and that naturally in the phase space in physics language. Okay, so now we have this notion of wavefront set. I need a bit more terminology. So if A is a bidistribution, say now in U and V, U or V are subsets some other Euclidean spaces, Rd, Rn, then this is called twisted wavefront set by a dash of U is defined by xi, y, eta. So these are now belongs to the cotangent bundle of T star U cross T star V, and of course dot, such that xi, y, eta, minus here, belongs to reference set of A. So it's just for convenience. If you want to avoid this minus, or maybe I put minus here, instead of writing minus here. Okay, so now we are ready to address this non-trivial definition of Feynman propagators. Definition, this is due to Strohmaier and Hermander in their Fourier integral operator 2 paper. So a propagator, Feynman, for the box which satisfy these two properties is called a Feynman propagator if, so now this is an operator, and due to standard theory of distribution, it has a Schwarz kernel, and I will use same later for Schwarz kernel and operator, hopefully you not mind. So if the twisted wavefront set we have just introduced there, now this G is the Schwarz kernel of F Feynman is xi belongs to E dot we introduced just before, M cross T dot cross M. So this is the diagonal part. So if you think in this way, this is T dot star M, and this is another T dot star M. Then this is the diagonal part. Okay? That's here, because xc and y, so you can think this x equals to y eta, and they all are same. So that's the diagonal part, and this is true for any propagator because that is basically mimicking the identity. Okay, now comes the more interesting part, or say what does Thematic say? What about the off diagonal? And that's given by xc y eta now belongs to T naught of M cross T naught of M. By this, maybe I also put it here. So we are in a Lorentzian manifold, and by okay, T naught at point X, M is defined as X naught, T naught belongs to T dot M such that they are like. Now you can glue these things up together, and then there's a bundle because we have a global hyperbolic manifold. So this is light cone bundle such that there exists a unique flow parameter S, which is either positive or negative in a way that this point xc can be related with y eta by a geodesic flow. So the phi is a geodesic flow on cotangent bundle. Okay. And for later convenience, I will use this off-diagonal part as a C plus minus, which is called forward and backward canonical relation because of geometric region. It comes as a Lagrangian submanifold. So, okay, so that's the definition. And now we ask this question. What Feynman wrote quite nicely, how about in curved spacetime? So before going there, I would like to slightly mention that, so the way Feynman started is actually included here. So what Feynman told, particle moves forward in time and antiparticle moves backward in time. Hermann-Rosse and Strohmaier definitions is also true, but of course in curved spacetime we don't have time, energy, but microlocally we have this notion, and then microlocal is true. And this basically mimics this part microlocally. Now, since Feynman was interested in quantum field theory, and this was invented in that context, one may wonder what it has to do in general for quantum field theory. So shortly, if we consider quantum field in a curved spacetime, then in general, you have lots of states, and the natural question is that what are physical states? And so far, the sufficient condition is Hadamard condition. So if you consider the so-called time-ordered product of classical observables, say Px, answer product Phi star y. So this is a quantum object, and you apply to your quantum state. If this is Hadamard, then this is how Feynman propagator is related. And this is due to Radziwiłłowski in his PhD thesis. Now, for physical reason, a state must be positive, otherwise we don't have positive expectation value. And that puts some condition. So in general, Feynman has nothing to do with positivity or negativity. It just satisfies these properties. But if we consider from this viewpoint, and then it is positive, then it also enforces something. Now we can play this around. Like if you have Feynman propagator with a specific positivity property that I would like to mention if I have time, then you can actually construct this state. So construction of Feynman propagator with this positivity also gives you a Hadamard condition or Hadamard state. Okay. Now we have our setups. Now let me mention the main theorem. So the Feynman or box. The first theorem, so just to repeat, Mg, as if here is globally hyperbolic spacetime. Let me use the shorthand. And we have the vector bundle, E over M. Now, since we are interested also to construct this Hadamard state, we need some sort of positivity. But in a bundle setting, in general, you don't have a notion of positivity unless you have a sesquilinear form. So we endow the bundle with a sesquilinear form. C vector bundle. And this linear form is such that our normal hyperbolic operator is symmetric. So under these three conditions, which are fairly general, one can construct a Feynman propagator for box such that the quantity W, which we defined minus I times Feynman propagator minus advanced propagator for box, is symmetric. And now if this linear form is Hermitian, then we have better result. If this is Hermitian, then the Feynman propagator can be chosen such that this quantity W is positive. And when this is case, so W mimics basically Whiteman two-point function, if you are familiar, and then this tells that this induces a Hadamard state. So this is me and Alex Strohmaier. This is hopefully published somewhere this year or later, but it's arXiv already there. So by this theorem, we have not only construct Feynman propagator, but with this positivity, we also have a construction for Hadamard state for any globally hyperbolic spacetime with your favorite bundle, which satisfy only these three very natural conditions. Now, before proving this result, I would like to mention that one can prove similar result for, say, more fundamental operators in Lorentzian geometry, namely for Dirac operator. So let me introduce a Dirac-type operators. So by a Dirac-type operator, we mean that it's a first-order differential operator. Again, I am in a smooth setting, so from a Lorentzian manifold M to a vector bundle E mapping to itself, which is first order, and its principal symbol satisfies this condition. So G, psi, and of course we have identity endomorphism. So I call it Dirac type because for the existence of this operator, we don't need any spin structure or anything. So no topological restriction, apart from it's a Lorentzian manifold, and Lorentzian manifold needs some topological restriction. Okay, now once you have that, you can actually have all these propagators, advanced, retarded, Feynman, anti-Feynman. I denote F, so this cross for these three, defined by D, and G cross. So then one can be tentative, one can be very, say, interested to apply this theorem to get Feynman propagator because we have just this thing, and then maybe also for later part the positivity and Hadamard condition. But there is the problem. So for a Dirac type operator, so we need this symmetry condition with respect to some sesquilinear form. Now, if you are in a Lorentzian setting, so in a Lorentzian spin geometry, the natural inner product with respect to which Dirac type operator or spin Dirac operator is symmetric is not positive definite. In fact, this is indefinite. So we can't have naturally a Hermitian form. However, we are in a globally hyperbolic setting, which means that we can write M isometrically R cross sigma, where sigma is Cauchy hypersurface. Cauchy surface. And given such a Cauchy hypersurface, and so given a unit normal covector zeta along the Cauchy hypersurface sigma m, assume that this form, so I use this Dirac bracket notation defined by principal symbol of Dirac-type operator with unit normal vector field applied to this and that, is fiber-wise positive. Okay, so now we have a notion of positivity, and then we can use this thing to go to similar construction. So let me give the former statement. That's our next theorem. F Feynman for a Dirac-type operator. Also in our paper. So as usual, we consider globally hyperbolic spacetime and a vector bundle over M with a sesquilinear form. And due to this principal symbol, we can cook up a Clifford multiplication, which make this bundle a Clifford module. So this is a Clifford module bundle over spacetime manifold M. So we assume, as before, D is symmetric with respect to this sesquilinear form. And then we have constructed, one can construct a Feynman propagator for Dirac-type operator such that S, so it's just a kind of counterpart of bosonic theory, if you want to think more physically. F Feynman minus F advance is symmetric. Moreover, if there exists a Hermitian form in this notion, so let me give it star, in this sense, then the Feynman propagator can be chosen such that S is positive, and then this induces a Hadamard state. So now both of these theorem has a predecessor. So there are other people who also constructed Feynman propagator and Hadamard state in different setting. If time permits, I would like to give an idea or the overview in the literature, in particular with people sitting in this audience. Okay, so now let me prove at least one of this theorem. So before I start proving this theorem, just I would like to mention all the Feynman propagators started from quantum field theory, but by now we know that they have other applications which is more general than quantum field theory. For instance, in Vasey's hyperbolic treatment, they occur naturally. Also in the Lorentzian generalization of index theorem, they also come naturally and plays a key role. So proof. So let me let's sketch the idea of the proof for Feynman propagator or wave type operator. So the proof is not short enough to discuss in next 30 minutes. So let me sketch the basic steps and then some of the main technicalities. So let me first give a roadmap of how the proof proceeds. So the idea is that first one construct a Feynman parametrics. Now, those who are not familiar, then a parametrics satisfy all these properties, but instead of just identity, if this would have a parametrics, it would be identity plus some smoothing term. And same thing here, identity, some other smoothing term. Both the smoothing term not necessarily be same. So in the first step, one construct such an Feynman parametrics, and then we keep going and prove the positivity as mentioned here, but in the level of parametrics. So instead of W, we will prove positivity for I times E Feynman minus G advance. I just write as a symbolically positive. Once we have a positivity, then we can go to construct the Feynman. Now, let me go the anti-chronological way. Say we have done this construction, or even this one. That means we have a Feynman parametrics. So once we have a Feynman parametrics, then there is a standard technique in partial differential equation literature to turn a parametrics into a true propagator, and that is just by using well-posed Cauchy problem. So I'm not going to discuss in detail of this part. Now, let me come back to here. So to construct this, it's a good idea, put it far over. Okay, so there are, of course, several constructions. The way we construct, we did a macrolocal construction, which is originally due to Dirac-type and Hurmander, and we generalized it for bundle setting. So I will mention precisely where bundle setting comes different than the scalar case. Before, let me again allow to have some black box. So one more terminology. So say U is a distribution and V is also a distribution. Now I will write U, this equiv sign, V, meaning that their difference is smooth. Now this is for distribution. And now what I am going to use for operators. So let me use, I will call it as a blue box of D1, where D1 is minus I times some identity matrix D by dx1. So I start from 1 instead of 0. Now what does this mean? Give me a while to just sketch how it proceeds, and then I will explain in detail what does it mean. But for the time being, just assume there is some blue box which can relate P and D1. Sorry, it's a box. D1 in that setting, but okay, it's not yet clear what is that, so just bear with me. Now, if this is true, then we can just write the retarded and advanced propagator for D1 is just Heaviside times Dirac delta. And from there, we can cook up this Pauli-Jordan-Lishnarovich commutator function, or in quantum field theory literature called causal propagator, which is minus retarded minus the advanced part. And in this case, this is just Dirac delta. But Dirac delta in the Euclidean part. Okay, so once we have this data, then we need something called a Fourier integral representation of this thing. So let me also introduce perhaps the last tool for today. So by a Fourier integral operator, we mean some operator A, which maps compactly supported function on a manifold N over some vector bundle, say F, to distribution on another manifold M vector bundle. So we take some element here, and then a V of X is just defined as, so just to differentiate right now, I just use this curly X, A, X, Y, V of Y. So I have considered everything densities, so there is no dy. Now the main thing is that if this, so this is a bidistribution in general due to Schwarz theorem. Now if this distribution has a specific form, then it is called a Fourier integral operator. And there is a name of this distribution, which is called Lorentzian distribution. So this is again due to Hermander. However, the idea of Fourier integral operator was also found in Maslov and some earlier references as well. But those are in a local setting and not in a systematic way. And Hermander took this and globalized it. Okay, so I'm not going to the general definition. Rather, for us, it's sufficient to know that locally we can write this A. So this is a distribution, but let me write just as a function. But it is a distribution. 2 pi, some factor, which is not important. So let me ignore. R to the power n. So this n has nothing to do with dimension of capital N or M. E to the power I, phi, x, y, theta. A, x, y, theta, d theta. So this is called phase function, by which we mean that this is homogeneous and can satisfy some property. Again, I'm not going to spell out those properties. You can look, for instance, like a Strohmaier lecture in this summer school, or Hermander's book, where every details are given. And this is called symbol. I am using polyhomogeneous symbol. Again, I'm not going to detail. Just for the timing, it's sufficient to know that if you take derivative with respect to theta, this has some nice decay property. Okay, so just remember this form. And if one has this form where this belongs to s to the power m plus dm, so this is dimension of m plus dimension of n minus 2n, n is this one, divided by 4, then we write this in Im u cross v, and something, this is called the canonical relation that we have seen. So once you have this phase function, then this can be obtained x dx phi, and for our case y dy phi. Again, you are geometrically inclined. This is a Lagrangian distribution, sorry, Lagrangian submanifold, but we don't need that. So now the whole point is that you can write this an oscillatory integral using Fourier, and then you will have a special case of what's written there. And then this is just I to the power minus half Rd cross Rd. With some canonical relation one can cook up. Again, the explicit form is not required right now. So let me carry on. Okay, now once we have this Fourier integral operator representation of causal propagator, then we use this blue box magic again. And this will give us Feynman propagator. Or not really, Feynman parametrics. And in fact, this is more powerful than just to obtain Feynman parametrics. This can be used for other purposes. So let me go the detail of what this blue box means. But before going there, how we proceed here. Now one can see that this is Dirac delta. So this is actually positive. If you put test function, then you will look that this is positive. And then you play again this blue box game. But now one has to do a bit finer. So this is called micro-localization. Micro-localization. Why it is called, we'll see. So we need some, say, refined version of micro-localization, And then basically one can prove this thing. So hopefully now it's clear. The main technical tool is this micro-localization. Now before give you what is meant by macro-localization, I must say that until this part was done due to Strohmaier and Hurmander, but they considered scalar operator with great generality where Cauchy-Well-Posner's name does not make sense. And if you look their paper, they wrote they don't see any way to fix this smoothing term because the only difference is a smoothing term. However, we are geometrically in a better situation because it's a globally hyperbolic case, so we have well-post-Cauchy problem, and then we could fix this smoothing term. And there are other ways to fix this smoothing term. One is by Dr. Vasi. He used a different method than us. And this part is a bundle generalization, provided you have a bundle generalization of micro-localization. So now let me give that. So yes, I just need micro-localization. So the basic idea is that, say we have again the vector bundle, but now just over a manifold, and we have a pseudodifferential operator, but this is properly supported over the manifold. And as usual, we have this D1, and we want to relate P with D1. Then the idea is that if we have this principal symbol scalar, and it vanishes at some point in cotangent bundle, and the Hamiltonian vector field and radial vector field are linearly independent at this characteristics points, then by a homogeneous version of Darboux theorem in a conic neighborhood of eta1, y eta1 to these points, x0, psi naught, conic neighborhood, you have a homogeneous symptomorphism. This is just a homogeneous version of Darboux theorem. And then you can actually leave this in the level of bundle so that the pullback of sigma p is just the first coordinate. Now the whole idea of micro-localization is to put this forward more in the level of operators rather than principal symbol. So if I carry on pictorially, we have RD, PK, and its map RD, PK. This is our D1. And here, compactly supported M, E, compactly supported ME, P. Now, there exists Lagrangian distributions so that this diagram commutes in this sense. So, x0, y0 is not in the essential support of A d1b minus p, and 0, eta 1, y1 is not in the essential support of b p a minus d1, where A is a full Lagrangian distribution given by M cross RD with canonical relation graph twisted with some homomorphism bundle due to the bundle character, and B minus M the other way, RD cross M graph of kappa minus inverse again the homomorphism bundle. So that's the blue box we used. So by P D1, that is what we meant. Now this theorem has been proven by Strohmaier and Hurmander for scalar cases. If you look at bundle cases, you need to consider curvature due to bundle and fibers because you can't identify fibers, and then you need to consider some connection. This is partly done in Denkers, but in a more say local like system of matrices, and we provide this theorem in a more say geometric fashion, considering a natural construction of geometric some bundles in appropriate setting, so that one can just use as a black box. So all the conditions are given, and then one can just use it and pick it. In contrast, Denkers' work is hard, so it's like in the text hidden somewhere. So thank you very much. Mm-hmm. Yeah, for instance, in usual spin Dirac, this is naturally satisfied. You don't need to put this assumption. So that's natural. In fact, this is motivated from spin Dirac. So for spin Dirac, this is just gamma naught, if you think. And then, but it's now in a more geometric fashion. Oh, yes, I forgot to write. Yes, future directed. Yes. Mm-hmm. Yes. Okay, so there are a number of ways, at least there are 4 ways to construct Hadamard states. So this is deformation argument, and then there is holographic, this one, and then the original Wald, Norwich, this idea. And all of this has some, merits and demerits. Now, you can use this thing without using any deformation argument. For instance, if someone wants to consider like perturbative quantum gravity, there one can't use deformation argument. But in principle, at least in linearized level, this should work. However, there are some situations where deformation argument can be used, for instance, for gauge theories, where you have gauge symmetry, and we haven't been able so far to incorporate gauge symmetry here. So at this point, it's not sure that whether this is inherently incapable to incorporate it. Maybe, so it's like under construction or under research, but so far it's not the case. On the other hand, this is completely macrolocal, so you don't need to consider any sort of like Cauchy hypersurface and how they match and this sort of thing. And so if you, and also for deformation argument, I mean, that's also very versatile. It's not like I'm taking something from there. So I would say both has its pros and cons. Something is better or more efficiently can be done in this setting or this formalism, and something so far is more amicable in the deformation setup. Okay, so that's basically, if we look at this characteristic set of box, then this is the light cone bundle. Now, if I draw this, so say this is the future. Okay, maybe start here, here. And this is the past. Now, Strohmaier and Hurmander shows that the number of parametrices for box is equals to number of 2 to the power number of connected components of this thing. So for this case, we have 2 connected. If dimension is more than 3, equals to 3 or higher, then we have 2 connected components, this one and that one. So we have 4 orientation, and we have total 4 exactly parametrices. So there are nothing more. And these 4 are advanced, retarded, Feynman, anti-Feynman. So if you want to think more pictorially, what retarded does, it takes something here and push everything in this way, and advance to the other way. And now Feynman does for positive energy macro-locally, takes in forward and backward, and anti-Feynman to the other way. So there is no more. However, if the dimension is 2, then you have actually 16, because you can have more, but that's a speciality of just dimension 2.